I'll no. Copy. I know what you're saying. Would it kill you if you could make the hyperlink a hyperlink as opposed to not a hyperlink? Anybody who's got a machine handy that can verify the announcement in Sakai is actually broadcasting this one? Ernie, I'm looking in your direction. Or it doesn't have to be your direction. I just know that you were working on it before, and I still feel bad. Or anybody using Sakai? Are we live?
Oh, I've had a question about the variance.
That's why we're here. I just want to make sure we're live. We are? Cool. Thanks, John. I'm just kidding, Bella. Just kidding. Yeah, that's why we're all here. That's why I'm here too. And if this were anything else, you know, maybe I wouldn't be here. But man, I'm going to be here until 6:30. I don't know what format works best. I know that at least one person in here has a question, and I would love to be able to. I would love to be able to answer all the questions. That's 2 hours to do it. There's a number of ways that could work most efficiently. The most important thing is for me to probably stop talking. I'm going to start by getting the questions that you have. You come in here, we're ready for questions, let me know, I'll put them in the queue. After that, I'm going to switch over to the overhead and try to do everything that we do today by hand, because that's how you're going to be doing it on the exam tomorrow. I'm going to use my phone as my calculator because I'm allowed to. You, on the other hand, are not. I'm probably just going to ask Siri to do my math, actually, because I realize I can do that lazy. Any other question? Question?
Is variance going to be on the exam?
Variance is certainly on the exam, but what are you going to be required or asked to do of that? I mean, Bella, what's the relationship between standard deviation and variance?
Isn't variance like the square root of standard deviation squared minus?
There's no subtraction.
Okay.
No subtraction. All right, let's start with this. What's the symbol for standard deviation? Population level.
S. No. Sigma.
Sigma. Right there, that's the standard deviation, right? What's the symbol for the variance? Watch step, watch step. What's the symbol for the variance? Oh.
Is it sigma squared?
It is. So effectively, there's 3 different metrics that we'll use to talk about dispersion. Standard deviation and variance are 2 of the 3. The other one is range. Range is just the maximum minus the minimum. But the relationship between standard deviation and variance is such that we'll often talk about them interchangeably, but we'll functionally use little sigma. The metaphor I tried to come up with today is like this. Is a hamburger a sandwich? Is a hamburger a sandwich? I mean, Allie says yeah. Why?
It has 2 pieces of bread and stuff inside.
Yeah. So for Allie, that's how you define a sandwich, is 2 pieces of bread and stuff inside. Who disagrees? Who says a hamburger is not a sandwich? Connor, why is a hamburger a sandwich? Because it's different on the menu. There you go. Well, are standard deviation and variance the same thing? Yes and no. In some sense they are, because the mathematical relationship between them, if I take the square root of the variance, I certainly end up with the standard deviation. So if I know one, I do know the other, and vice versa. Like knowledge of one is knowledge of the other. So if I'm talking about a distribution and I want to say it has a lot of variety, I'm probably going to say it has a large variance. But a large variance just the same as well means it's a large standard deviation. If I give you a variance of 2,000 something squared is the appropriate units. But that's also why we don't use variance as the statistic. Standard deviation is what we use because it's in regular units, not like dollars squared or miles squared. Yeah, I think that's about as much as I want you to know about variance and standard deviation. Just know that, like, if I'm talking about one of them, it's about the discussion and conceptually about what dispersion for those metrics is, as opposed to I'm asking you to do some calculation with the variance. Correct.
No, yeah. Bueno, no. Is that okay? In the midterm from spring 2016, the 25th, it said the symbol that represents the square root of the population variance. Will that be again the sigma on square?
Yeah. So this one is population variance, and if I take the square root of something squared, I get the standard deviation.
Ah, so it's sigma only.
Correct. Is what happens if I start with sigma squared. This is what happens if I start with sigma squared and take the square root of it. Square root takes the square away, and I'm just left with sigma.
Ah, okay.
All right, more questions. Get them up, get them up. Questions. Yeah, bring. Fall 2015 continuous probability. Adding that to the queue. What's with the brightness? I feel like it's too bright. All right, fall 2015 continuous probability.
Spring.
2015, 41, 42?
Yeah.
Spring?
Yeah.
Spring 2016, number 40.
Fall 2015, 34 to 36.
That's the slot machine problem, right?
It's all about the apple.
About the
The apple?
apples?
Yeah, it's like older dude, younger dude.
Oh, the apples. Right. No, it's contingency. Can do.
Fall 2015, 24, 25.
Fall 2015, 24, 25?
Yep.
Fall 2014, the 31.
Number 31, Victoria?
Yes.
Number 41 on spring 2015.
That one? 41 in spring 2015?
Oh, sorry.
No, just want to make sure it's, no, just making sure.
Oh.
All right.
Spring
Yeah.
2016, number 10.
True false question?
Yeah.
What's the true false question, Kat?
A drawback of the variance is that it can be dramatically affected by a single operation.
Oh, no, that's not a drawback. That's a feature. Actually, the answer to that one is false. So the question from spring 2016, this is the same conversation as the dispersion before. The difference between something like the variance or standard deviation, this is one of those cases where I'm just going to talk about them as if they're the same. When you calculate variance, you have to take into account for each observation, how far away is it from the mean? So each and every observation is used in calculating the variance. How many values are required to calculate the range? Even if your data set has 100,000 records in it, it still only takes 2. The minimum and the maximum. So you could have 100,000 records, 100,000 observations, and 99,999 of them are identical. 9,000 of them, there's no variance. But one of them is different, and it's different by a lot. The range suddenly appears as though you have a giant dispersion. But if you calculate the variance is still going to stay small because the variance says, yeah, sure, you've got one that is very different from most things, but most things are the same. So in general, there's not a whole lot of variety in the data. So a single value typically does not affect the variance, although a single value can dramatically affect your range.
Makes sense.
Honor?
Spring 2015, 44 to 46.
Spring 2015, 44, 46. Spring 2015. Was spring 2015 the one with the slot machine? That seems about right. With the slot machine and the binomial probabilities?
Yes.
Spring 2015? Yeah. That was a rocky one. People were not happy with that midterm, but it's a lot easier than that. For those of you who stopped by this afternoon and discussed that problem with me, of which there were a number, it's pretty straightforward, ultimately. But a lot of times what happens is that students will see something that they haven't seen before, and because they haven't seen it before, they panic, they assume they can't do it, they don't rely on the fact that we've been practicing, and they don't have faith in the fact that I wouldn't ask you to do something you can't do. On tomorrow's midterm, you may see something you haven't seen before. Now that I've got your attention, trust me, you can do it. It's as straightforward as the stuff we've been doing. But the difference is that you haven't exactly seen it set up like this before, but you've seen the same problem. It's just got a little bit more context. I don't want to spoil the exam for you, but it isn't all that different from what you've seen in past exams or that we've talked about in class. Just may require you to take your time a little bit more, but don't be surprised if you don't see exactly what you've seen. Again, why I get anxious about using old tests as prep material is that students will say, I can do spring 2016 with my eyes closed. And I'll say, that's great, but you're taking fall 2016 and you got to take that one with your eyes open. So try to have those skills handy. We got a bunch of stuff in the queue. I think I'm going to go through these in some particular order. How about the order that they're listed on here? I'm going to stay within one exam, even if that does require changing gears from continuous to simple to contingency tables and stuff like that. I will be switching gears, but I'd rather, it's gonna be easier to navigate if we stay in one exam. If there's more questions, let's get through these first and see how far that takes us. And we'll go from there. We'll start with fall 2015. Continuous probability and contingency tables. We'll start with the one that's got the contingency tables on it. So this is a bigger contingency table than you've seen in the past, but it's not all that different from what we've worked with in the past. It's got more categories. Five different types of people, 5 different types of apples. This is effectively saying that a number of different people have different favorite types of apples. Where'd the question come from? Who fostered? Yeah, Yanni. All right. So let's walk through this one, Yanni, shall we? Okay. Question 31. Given that a person is a lady and not a child, what is the probability that their favorite apple is not a Fuji? There's lots of yeses, nos, nots, this, or, and that. There's 5 types of people up here. Which type or types of people do I care about?
The older lady and younger lady.
Older lady, younger lady. There's a total of 259 people between those two groups, right? Yeah. So whatever probability that we're looking for, because we're looking for a probability, that statement says, what is the probability? So the answer better be a probability. By the way, 3 people on the quiz provided me probabilities that exceeded 1. Probability cannot exceed 1. If you see a probability that exceeds 1, your answer is wrong. Anyway, the question says, what's the probability? So we need a probability that their favorite apple is not a Fuji. 2 ways we can go about this. One way is to find out which of those apples up there is not a Fuji. And that's a whole bunch of different types of apples. On the other hand, I know that for those 259 people, 54 out of 259, is that 54? I think that's 54. Yeah. 54 say Fuji is their favorite. So if 54 out of 259 have Fuji as their favorite, what proportion don't have Fuji as their favorite? But I don't care about 571.
Oh, wait, no, sorry, no, 205 out of 259.
Yep. So it's the complement of 54 over 259. 205 out of 259, is that right?
So it's 28 out.
That's 205 divided by 259.
That would be about 0.7915.
If it's 205 over 259, I got 79%. Did you get 205 or did I do some subtraction wrong?
That's right.
All right. 79%. 32 says, what percent of older dudes say that Gala is their favorite apple? Yanni, who do I care about in 32? And only the older dudes. So whatever probability or proportion I come up with better be out of 175? Yeah, should be out of 175. Say that Gala is their favorite apple, 29 out of 175. And that should be your expectation on problems with contingency tables. There will often be either a comma-separated interrupters or little phrases which say, who exactly are we talking about? Everyone or just a small group? Just the older dudes or just the ladies who are not children, etc. 33. What proportion of unattended children say that their favorite apple starts with the letter G? So this is proportion of unattended children, and how many unattended children are there? 31, which is many or few, depending on your attitude towards how much attention children should get. But the question is, starts with the letter G. Golden Delicious and Gala. Looks like 8 out of 31, or just over 25%. So those are the first three. But when we get to 34, 35, and 36, the nature of the problem changes. What do these problems turn into when I give it 34, 35, and 36? Jan, you know that? How about this? If I said, I'm going to ask you to take 5 coins and flip 5 coins, how many times do you expect tails to appear? Do you know what context we've walked into there? The type of problem that is.
We're doing class or something.
Binomial probability experiment. And in fact, that's what 34, 35, 36 are. They're binomial probability experiments. So I'm going to have a fixed number of trials. Let's say I'm talking to 10 older dudes, 100 younger dudes, or 4 ladies. I have a fixed number of trials. For each one of these, there's a probability of success. The probability of success isn't just given to you like Tuukka Rask's save percentage. You may have to derive the probability from the table, but then use that probability as your success probability. Case in point number 34. Sure, I'm going to talk to 10 older dudes. And I know that my random variable x is going to be 5 because it's exactly half of 10. I'm going to talk to 10 dudes, or whatever it is, 10 older dudes, not pictured. But when I talk to those 10 people, I'm going to ask for the probability that for exactly half of them, they're going to say yes to something. What is that thing they say yes to? Their favorite apple does not start with G. So, to determine the success probability, the first thing I need to do is say, for the older dudes, of which there are 175, the probability that their favorite apple does not start with G, that starts with G, that starts with G, that one doesn't, that one doesn't, that one doesn't. So, 56 plus 49 is 105. 105 out of 175 is 60% or 0.6. So if I'm talking to an older dude, there's a 60% chance that their favorite apple does not start with G. There's a 40% chance that their favorite apple starts with G. But that only applies to older dudes. Different types of people will have different favorite apples. But the question in 34 says, I'm going to talk to 10 dudes, n is 10. What's the probability that for half of them, x equals 5, their favorite apple does not start with G? Pi is 0.6. N is 10, x is 5, pi is 0.6. N is 10. N is 10. Pi is 0.6. X is 5. 0.201. That's the probability given 10 trials that exactly half of them succeed when given a 60% probability of success. John, tables are provided. By the way, we got this going, so it's available too. Yeah. Question? A little louder, please. Because there are 100, the question is, why does pi equals 0.6? Pi equals 0.6 because there are 175 people in the category. Are you okay with that much? Yeah? There are 5 different types of apples. Some of those apples start with G, some of those apples don't start with G. There are apples that don't, Cortland Empire and Fuji. The total number of people who say that their favorite apple is one of those 3 is 105. So the probability that someone says from that group, the probability that from that group someone says their favorite apple is one of those is 0.6. That's why pi is 0.6. $35 is the next one. Yanni, we set?
Yeah, I get it.
All right. 35, we're now going to ask about an expected value. And I know it's expected value because the problem says, what value do I expect? Or how many do I expect? That means expected value. Now I'm going to talk to 100 people, and I want to know, of those 100 people, how many are going to say that their favorite apple is a Cortland or a Fuji? What group of people in 35 am I talking about?
The younger ones?
Younger dudes. How many younger dudes are there?
106.
106. The question says, I'm going to talk to 100 of these younger dudes. Some of them are going to say their favorite apple is Cortland or Fuji. Some of them are not going to say that their favorite apple is Cortland or Fuji. Of those 106, how many said that their favorite apple is Cortland or Fuji?
53.
53. So 53 out of 106 as a proportion is 50%. Means that 50% of younger dudes I talk to identify Cortland and Fuji, or Cortland or Fuji, as their favorite type of apple. So I'm going to talk to 100 dudes, 100 younger dudes, and I expect that half of them are going to say that's one of their favorite types of apples. How many, then, in terms of a number of younger dudes, how many of those younger dudes are going to identify that apple as their favorite type of apple? Nope.
I was asking for probability.
Nope. The probability is 53 out of 106, or 50%.
Yeah.
So half of the younger dudes, whether it's half of 10, half of 1,000, or half of the million, half of younger dudes say that Cortland or Fuji is their favorite type of apple.
Right.
I talked to 100 dudes. Half of them are going to say that it's a favorite type of apple. What's half of 100?
50.
I expect that 50 younger dudes are going to tell me that their favorite type of apple is one of those 2.
Oh, okay. Yeah, I get it now.
I use the table to determine the probability, pi. I apply it to a certain sample size, n. N times pi tells me my expected value. 36, we're still going along the same narrative. We're going to talk to 4 younger ladies. So we're going to develop some probability using the 125 younger ladies. My favorite apple is Fuji, so I'm going to ask them if their favorite apple is Fuji too. But we want to know the probability that at least one of them says yes. So there's 5 younger ladies. There are 6 different possibilities. None of them say yes. 1 of them says yes. 2 of them, 3 of them, 4 of them, or 5 of them says yes. That's 6 different possibilities. What I want to know is the probability that at least one of them says yes. It doesn't have to be all 5. It could be 1 or 2 or 3 or 4 or 5. As long as it's not none of them, the complement rule, as long as it's not none of them, we're all right. So the first thing we have to do is determine the probability that for younger ladies, Fuji is their favorite apple. What's the probability that for younger ladies, Fuji is their favorite apple? Yeah, 5 quarters. 5. So 1/5 or 20%. 20% of younger ladies say that Fuji is their favorite apple. And I said I'm going to talk to 5 of them. So n equals 5. 20% success rate. The probability that none of them say Fuji is their favorite apple is about 33%.
Aren't there 4?
Are there 4? Sorry, as you get older. No, you're right. Thank you. There are 4 younger ladies. The probability that none of them say Fuji is their favorite is 41%. The probability that one of them say Fuji, could be the first one, could be the last one, could be the third one, can't be the 5th one. Why can't it be the 5th one? Because there's only 4, yeah. Could be the first, could be the second, could be the third, could be the 4th. 41% chance exactly one says yes. But what I'm concerned about is at least one, which is either the sum of 1, 2, 3, and 4, or the complement of none. 1 minus 0.41 is 59%. It's a 59% chance at least one of them, could be 1, could be 2, could be 3, could be all 4. 59% chance that at least one of them says, yes, my favorite apple is Fuji too. It's a binomial probability experiment with 4 trials. Pi is 0.2, and x is 1, 2, or 3, or 4. Who's that?
Drew?
What's happening, Drew?
Should we put 0.59 or 59%?
That's a good question. I have been diligent with my specification. 59% or 0.59 is fine with me. If I say round your probability to 2 decimal places, what I'm saying is 0.59, but I can also read 59%. 59.29% is too far. That's not 2 decimal places, that's 4 decimal places expressed as a percent. Z-scores go to 2 places. If you calculate 1.75 as your z-score, use 1.75. Don't use 1.8. Our table accommodates 1.75. Please use 1.75. Of the 5 groups of people listed here, the one who is most likely to say Empire is their favorite. Oh, thanks, Drew. I didn't know you were just leaving.
I'm gonna be back.
All right, cool. He showed up for one question, rounding, and then he's out. To find out which group is most likely to say Empire is their favorite, 40 over 175, 20 over 106, 39 over 134, 33 over 125, 10 over 31. Whichever of those proportions is the highest is the group we expect to say that Empire is their favorite. I don't know, probably unattended children. That's my answer oftentimes, though. Who started that fire? I don't know. Unattended children. It's funny, right? I'd say it the second time. I ruined the joke. All right, I'm going to move on to the next ones. Staying towards the end of fall 2015, that was a good semester. Although I did have to retire my car. Oh boy, that was a sad day. Whose questions said fall 2015 continuous probability? Frankie, that's you? All right. Welcome to Thunderdome. So we're going to go through these questions. I want to be able to write, so I'm going to switch to the document camera, but I'm going to keep these questions on the center screen, document stuff up here. If you're following along at home, follow along. So my car, etc. There's a couple pieces of essential information in this problem, Frankie. What are the pieces of information that are going to help us solve this problem? The mean is 180,000. Sounds good. Yeah. Now we're in thousands of miles, so I'm just going to use numbers as such. But when the question comes down to how many miles, you better believe I'm going to tack on the 1,000 miles as the unit of measurement. But it's easier to work with numbers like this than having to write out a bunch of zeros after that. What other piece of information?
237,000 miles.
Yeah, that was my car. One more piece of information. No. Yeah, current mileage on 96 prisons is normally distributed. We need that piece of information so we can draw the picture. So we can draw that picture. Where the mean is in the middle. What's the value of the mean, Frankie? That's 180,000 miles, and that's a raw score. What's the z-score of the mean? When? You sure? Cool. All right. That's just some basic setup on here. 38, according to the empirical rule, approximately 95% of all geoprisms still on the road have between what two mileages on them? You got this one? Okay. So this is a normal distribution. In a normal distribution, we are allowed to use the empirical rule. The empirical rule says if you start at the mean, add 2 standard deviations, subtract 2 standard deviations, in between your arms is 95% of the data, or 95% of the cars. So if I start at 180, subtract 45, and do it again, that's like subtracting 90. Start at 180, add 45, add 45 again, it's like add 90. So between 90 and 270,000 miles is where 95% of the cars should be. 5% of the cars are going to have either fewer or more, so less or more miles on them. Yanni?
Have you added at least tracking that 45 twice because it falls between two standard deviations?
Yeah, 2 standard deviations. So we're gonna do 2 times 45. $90 to 270.
How do I write my answer from, sorry, 90 to the rest?
Yeah. So I don't know what that is. 38, 37. Just say 90 to 270,000 miles, or 90K, 270K, or 90,000 to 270,000. That's interval notation. I can read either of those. K is generally the acceptable symbol for 1,000. That was Chick-fil-A. Apple theme today. Into apple flavor combo. You ready for the next one, Frankie?
Yeah, I was just confused on how long the answer key was.
What did it look like on the answer key?
I think it looked like 90,270. I guess it was just a combo.
It's probably interval notation that throws you off. This comma separates 90,000 from 270,000. Interval notation can sometimes look awkward because you've got all these commas floating around, which is why if we're working in thousands, you generally use something like a K or 1,000 so you don't have all the comma and the floating zeros. 38, 39. When I retired my car, and what percentile of prison still on the road was my car? I've gotten either better or worse at speaking English than I have been or was before. My goal is not to have awkwardly worded questions. My goal is to be able to provide for you an opportunity to demonstrate that you know how to do this without having to deal with my words. What I want you to do here is to convert my raw score to a percentile and tell me what percentile my car represents. If that's the question I ask you, Frankie, is that easier to understand than the way this question is worded? Well, whether it is, that may be how you're going to be asked. Let's step through the process. Process has 3 steps, 4 parts. We can either start with the raw score, convert it to a z-score, which will help us get an area that we can turn into a proportion, probability, or percent. In this case, for 39, we need some sort of percentile. We're going to use a formula to go between these 2 things. We're going to use a table to get between those 2 things. We're going to use a picture to get between those 2 things. And for those of you who are hanging out this afternoon, I mean, we played with the picture a lot. I even tore up some paper. But I think by the end of it, we started to see what the real big purpose of the picture is. So, gentlemen, if we do something and I leave some part out of our discussion, I found it fruitful. I learned a lot about how to talk about myself, but I don't want to forget it. So if there's something that resonated with you from this afternoon that you want to pepper in, please do so.
With 39, are we finding the answer for 40?
Yeah.
Okay. I thought that I was just kind of thrown off.
Yeah. So I've also gotten better at asking questions in the appropriate order. Yeah. No, like this raw Z area proportion stuff, like I wasn't teaching that my first semester here. It's this dialogue between student and teacher that helps me understand what's useful. And this has provided utility, so I keep it around. Yeah, but you can also expect, so in 40, you got to find the z-score, which is effectively convert my raw score of 237 to a z-score using the z-score formula. Z equals x minus mu over sigma, or 237 minus 180 over 45. What's the z-score? 2 decimals, Frankie. 1.27. Confirmation? You. Because my car, which is somewhere over here, even if it's not to scale, had 237,000 miles on it, which was 1.27 for a z-score. Hey, that's the answer to number 40, is 1.27. I like to ask questions with those multiple parts, as I mentioned a number of times, and even on some of these quizzes, was, oh, I see what you did there. You picked the wrong sign, or you added 0.5 when you should have subtracted from 0.5. I can do a little bit of detective work there, but it's easier for me to do the detective work if I ask you for the pieces along the way. And you know what pieces I'm going to ask for along the way. So get used to providing them. Yanni, yeah.
You don't want to right? You just want 1.27.
2 decimal places. Z-scores round to 2 decimal places. 1.2 is not 2 decimal places. That's 1 decimal place with a small front end. 102.2 is not 4 decimal places. 1. 1.27. Now that we've got a z-score, we're going to use the area. Our table can only accommodate areas between the mean and some z-value. There are other tables out there which accommodate different areas, but I like this one, so we use it. When I go to this table to look up the area that's shaded on this picture, I'm going to get a certain proportion, and that's the proportion of cars which has between 180 and 237,000 miles on it. Whatever percent that is, when you go to the table and you look up 1.27, which is sort of like 1.28, which is right around 40%, I think. What do you get for an area for 1.27? Yeah, Connor? Or anyone who's loud?
0.398.
0.398? 0, thank you. That means about 40% of cars have between 180 and 237,000 miles on them. The language I've used and the way I've used to describe this sometimes is that we basically at this point have 3 parts in our picture. A, B, and C. And we just found the area for B. We can use the area of B to find the area of C, because we know that B plus C equals how much? Or what proportion?
50%.
50%. B plus C equals 50%. If I get rid of B, so I subtract 39.8% from 50%, I'm left with the tail, which is around 10%. But for our question, which is what percentile this puts me in, the area is 0.3980. The picture tells me that everything over here is what indicates my percentile. The 10th percentile is above 10% of the other cars. The 50th percentile, or the median, is above 50% of the cars. My car at 237,000 miles is above a certain percent of other cars. Frankie, what percent of other cars does my car have more miles than? Yeah. A plus B, 50% plus 40%, gets you 90%. My car, 90th percentile. Question 40. There's my Z-score. 41. What mileage would indicate a car with the fewest 1% of mileage of these cars still on the road? I mean, I know I'm a big fan of prepositions. Prepositions are good parts of speech. In, out, over, above, under, between. Like, those are good things. I use too many in there. How about this? I want to know what mileage is associated with the first percentile. Frankie, can you give me a mileage associated with first percentile if I ask the question that way? Where on this picture is the first percentile going to be? In section A somewhere, in section B somewhere, or in section C somewhere? In section A somewhere. Over at this part of section A or over at that part of section A? Towards the tail, because the first percentile is going to cut off the bottom 1% from the top 99%. I'm going to call this section, that's a lot of letters already. All right, I'm going to call this section D. This little part right here is D. And this whole section here, I'll call this one E. So A is all of this. D is this little tail and E is in here. I need to find E. I need to find this section between the mean and the first percentile. I need that area. Why? Because I've been given a proportion or a percent or a percentile of the bottom 1%. And now that I've drawn that on my picture, I need to find this area because it's similar to the area that my table provides if I look at it through the piece of paper. Same shape. Frankie, what's the value for E? The area between the mean and the first percentile? Express that as a four-digit decimal, please. Yeah. 0.4900. So we put the first percentile on the picture to get an area of 0.4900. No Browns hat today, and nor can I borrow Drew's New England hat. I gotta find a Z-score here. Area's on the inside, Z-score's on the outside. An area of around 0.49. I think we just may have done that. Something in there. I'm going to choose 0.4901 because that's pretty close. I can't find exactly 4900, but I can find 0.4901. See, those are close. And the associated Z-score with that is the more important piece, which is 2.33. And this is the Z-score. Having a picture allows me to draw a really bad negative sign. Negative 2.33. And then the last thing I do is put this into my formula. This formula, algebraically equivalent to this formula. Mu is 180. Z is negative 2.33. Sigma is 45. And that's great because 0.33 is a third, and a third of 45 is 15. So I got two 45s and 15. That sounds like 90 and 15, which is 105. I subtract 105 from 180. 75,000 miles. Talk to me, Frankie. How much of that are we going to keep with us tomorrow? We got 3 steps. First one is drawing the picture. Second one is going to the table and going either from an area to a z-score. But if you can do each of these 3 steps independently, you just got to know how to put them together. Any part of this you want some more clarification on? Why do you keep going away? And as it turns out, the z-score here, negative 2.33 as well. It's the same thing before, that those two things were backwards. 43 and 44, for the sake of time, I want to be able to just say you would swap out 180, put 50. If you put in 150 and calculate, watch that, and calculate this percentile again, but instead you had 180 or 150 here, that's how you would get the answer to 43. For 44, where I give you a variance of 2,000 miles squared, because miles squared is the appropriate units for variance. This is a concept question disguised as a math question, because the square root of the variance is the standard deviation, conceptually, and in this case, numerically. The standard deviation is 45. What's the square root of 2,000? Rounded to the nearest whole number. 45. So if I changed the standard deviation of 45 to a variance of 2,000, nothing changes. I mean, it changes a little bit, like scraps, but grand scheme of things, Jeff's just trying to be wily. Not wily, but like the coyote.
So would we just write no change in that?
That could be an appropriate response. And I think Allie's question is a really good question. Sorry, sometimes I have trouble controlling the timbre of my voice. Yeah, so if you're presented with a question and the appropriate answer is something like no change, or it's different, or less than, or the same as, provide that as the answer. Now, granted, the answer sheet has small blanks, so you don't get to write an essay, but you can write no change. You can write there is none. You can write less than. Ain't no problem with that. That's still a short answer. But that's a very good question, Alan. Andrew. Which one? 43? It's the same problem as we did with 39, but with a different mean. Yep. Other way around, 237, it's x minus mu. So 237 minus 150 over 45 gets you a z-score, gets you an area, gets you a percentile. That's all we're doing. Okay, I'm going to call it for that particular exam because we got more questions in the queue and we're an hour in. Shake it out and get loose. How about let me see what's on fall 2014 real quick. I feel like that's some low-hanging fruit. Because if it's one of these old questions, I can just tell you, don't worry about it. I don't know if that's the case here. Oh, it's the Tuca problem. Victoria, were you asking about this one?
Espérate. That one is.
Fall 2014, number 31.
Yes. I didn't know if to go from 10 to 4 or from 0 to 4.
Good. That's a good question. That's a good thing to bring up. This is a pretty good question too. So let's walk through this one. In this particular problem, we're faced with a situation that Tuukka Rask is a goaltender. His job is to keep the puck out of the net. Everyone else's job is to put the puck into the net. And if you're really good at this, they let you carry this big silver trophy around, and then you skate around with it, and then you get to wake up every morning and go, good golly, Phil Kessel is a Stanley Cup champion. How great is that? I mean, if you wear the right black and gold, that is. But for Tuukka, well, he's got a job, and his job is to keep the puck out of the net. Everybody else has a different job. So we can actually think about this in two different ways. One is that we can say saves. Or we can also talk about goals allowed. We know that this entire problem uses a scenario where n equals 10. And if you want, I can just give you the sheet when we're done signing it. Yeah. 28 to 31. If you want these notes, I can just give this to you if you don't. The probability of success for Tuukka is 0.9, because we know that 90% of the time he keeps the puck out of the net, and we call that a save. But on every shot, there's either a save or a goal. So we could also look at it as 10% of the time he allows a goal. 90% of the time he saves it, or 10% of the time he allows a goal. Either way, you can talk about it either way, but the truth of the matter, it's the same thing. Still with me?
Yes.
Because sometimes there's a relationship between these probabilities, and this is a complementary relationship, and we call it success or failure. To some, success is a failure to others, and so on. Maybe a concept that you see again in your future. I don't know. For question number 28, we're asking the question, use the table to determine the probability that he stops all 10. Here, I could say, given 10 attempts and a probability of success of 0.9, X is 10, such that it is 10 saves. Or, given 10 shots, and the probability of success is 0.10 that a goal is scored, X is 0 goals. 10 saves out of 10 shots is the same as 0 goals out of 10 shots. Can you do this with the table? If I just gave you those numbers, you can look them up.
0.3 for 10.
Cool. For 29, determine the probability he allows at least 1 goal. Maybe I start over here, because we're talking about 10 shots, and since the question is framed as goals, I'm going to use the probability for goals, and X is at least 1 goal. So 1 or 2 or 3 or 4 or 5 and so on. To put that in saves, the the probability that he allows at least one goal means that he makes all the way up to 10. No saves, 1 saves, 2 saves, all the way up to 9 saves. But if he makes 10 saves, he did not allow a goal. If I were to do this problem, I would probably choose this one because it's 10 shots, 10% chance of a goal. All of those represent at least one goal. And then I would do the complement here. So I come to the table, say for n equals 10, pi is 0.1, I want x is 0, and then take 1 minus 0.349. For 30, determine the probability he allows fewer than 4 goals. Again, goal allow is separate. N is 10, probability of allowing a goal is 0.1, and we said what? Fewer than 4? Now, I could keep doing these back and forth on both sides, but the fact that a 90% save percentage is 10% goals allowed, anytime I see the word goals in the question, I want to just go ahead and use the goals side of the sheet. It just makes it easier because now I have to think about what's the equivalent of this. That would be 10 saves or 9 saves or 8 saves or 7 saves. Why not just keep it in terms of goals, which gets us to 31. Determine the probability he allows more than 4 goals. More than 4. There we go. More than 4 would be the same as he makes no saves, 1 save, 2 save, 3 save, 4 save, 5 save. If he makes 6 saves, he allowed 4 goals, and 4 goals is not more than 4 goals, so that's where we stop. But that would be 5, 6, 7, 8, 9, or 10 goals.
Misunderstood. Thank you.
It's a good thing to understand for tomorrow. Let's move forward. Spring 2015 is next. Spring 2015 is next. No more contingency tables, are we? Good. This wasn't one of the solicited questions, was it? Rhino, what's up?
I have a question on
Hold that for right here for 30 seconds. Who had a question about spring 2015? I got, it says 41, 42, and some more than 40. All right, 41 and 42. 40, 41, and 42. Ryan, question, and then we'll go to 40, 41, 42. True. I mean, false. I don't know. Do I have to false or true bias?
Well, I don't prefer way because I know empirical will only go to normal distribution,
Yep.
but is it fair to say that you can only convert to Z-scores, or again, you only convert to standard scores when you do normal distribution?
No.
Okay.
Any raw score can be converted into a standard score, regardless of the shape of the distribution. So any distribution that can be converted to standard scores is any distribution. False.
I have another question about the empirical rule.
Okay?
Like, on another test, it says the primary condition for the application of the empirical rule is identifying that the distribution is a standard normal distribution. Don't you have to know that it's a standard normal distribution in order to use the empirical rule?
No. The standard normal distribution
That's not normal.
is a normal distribution.
It's not, it doesn't have to be standard. That's like a different thing.
This
Yeah.
This is the standard normal distribution. It is a normal distribution where the mean is 0 and the standard deviation is 1. Now, there's lots of normal distributions, but when we convert in regular old normal distributions about my car, about the apples, about whatever, we convert them to the standard normal distribution so we can use this table. And the thing we use to convert raw scores to z-scores is a formula. So I convert 180,000 to a value of 0 because it's the mean. I convert 237 to 1.27 because it's the same distance away of 1.27 standard deviation units. In the standard normal, we just say 1.27 because we're in the standard unit. Okay, this is a special one. This is what we want to convert stuff to. I feel like I dropped the keyboard, but this is right. Let's see. False, true, false, false, true. False, no, true. Yeah, it can, true. Expected value of any, see, here's another one of those, just another way I swap out these words. Number 7, the expected value of any normal distribution is n times pi, true or false? It is not true, it is false. I know, right? Because this is any normal distribution. What sort of distribution does it apply to? Binomial distribution. So I can swap out n and x and pi. I can swap out normal with any or binomial. Or, yeah, each word counts. That makes some headaches. And I want so many more. All right, let's go to 40. Every now and then Taylor gets to hear me come in and talk to Kristen because Kristen and Taylor work in the GA office together. And I'm always in there begging Kristen to come back and help me, but she refuses every time. Hey, points, sports. 39, what would be most useful to determine if this data is normally distributed? Histogram, you look at the picture. Give me a histogram and I can tell you immediately if this is normally distributed. All right, let's assume it is normally distributed. Let's see, Ryan, you were talking about 40, yeah? And then who wanted 41 and 42? Christina, all right. Oh, gotcha. N is 31. I think that helps. I think I forgot, I think it's, yep. Hard to do these things if I leave out a piece of information. And I think this was a case where I left out a piece of information from the exam. I think you needed to know the number of games played. Let me contextualize myself again real quick. First of all, I give you a normal distribution, and it says so right there. Oops. Says normal. The mean is 74, but you have to calculate the standard deviation given a variance of 132 p squared. What's the square root of 132? 11.5. Sounds good. Thank you, John. So my standard deviation is 11.5. I'm working now in a scenario where mu is 74, sigma is 11.5, and I've got a normal distribution. All right. Do the same stuff we always do. The number of points scored is normally distributed using this data and your knowledge of continuous probability. What proportion of games did the Friars score fewer than 60 points? X is 60, mu is 74, sigma is 11.5. 14 divided by 11.5. Let's not get lazy, Jeff. I know it's late, but these kids pay their lot of tuition bucks to come here and listen to you talk. To yourself out loud. Mu is 74, sigma is 11.5, which I got by taking the square root of 1. Mean standard deviation, it is a normal distribution. And for question 40, x equals 60. I had a normal distribution. The mean is 74 points. Z-score of the mean is always 0, and we're sure of that. 60 is a raw score. Raw scores get converted to Z-scores using the formula, which allows us to get areas from the table so we can determine a proportion. And the question for number 40 is, what proportion of games did the Friars score fewer than 60 points? Fewer is different from the word less, because fewer is used to describe discrete data, and less is used to describe continuous. Points, being that you cannot score a half a basketball point, are discrete. So it's important that I say fewer than 60 points, because you cannot score less when the measurement is discrete. The difference between discrete and continuous is that you count discrete things and you measure continuous things. It's a good question, Alan. Anyway, Brian, what are you next? I have a Z-score yet. What's the Z-score? What's 14 divided by 11.5?
That would be about 1.2173.
About. What did you say? Yeah, so first of all, negative, good work. Second of all, round it to 2 places. You're wrong twice, Siri. 2 wrongs don't make you right. Negative 1.22. Brilliant. Now that we have a Z-score, we can take that to La Table to find the area. And I don't have a negative Z-score. I think we're over that at this point. 1.22 is my Z-score. 1.22. Did you get 0.3888? I'm looking at you, Rhino. Yeah? I've effectively have 3 pieces now, A, B, and C. Which one of those areas represents the proportion of times the Friars score fewer than 60? So how much is in A? Nope. Point 1112. 1112. Yeah. The area that we got there was 0.3888, which means the proportion of games the Friars scored fewer is, if we round that to a whole percent, is 11%. 40 is 11%. And 41, the Friars scored fewer than 60 points 4 times in the 2013-14 season. What is the difference between the proportion predicted in the previous problem, 11%, and the actual observed proportion? But we don't know because there's no given to you how many games were played. We know that 4 times that happened, but we would need to know how many games they played, and I think I probably made up like 31. Anybody here manage a basketball team, play on a basketball team, go to a basketball game, go to all the basketball games? How many games? 30 sound reasonable? 31? I want to say 31. What year did you guys win the Big East? That season, right? So you would have played a few games in the tournament. Connor? 34? Cool, thanks. So for 41, N equals 34 games, and then the proportion of games 4 out of 34 is 2 out of 17. How much? 0.11 again. So the actual proportion of times the Friars scored fewer than 60 was 11%. In 40, we also said 11%. So for 41, what's the difference between those two? What's the difference between the two?
Like 0.76%.
Yeah, around 0%. So 0.76%. So somewhere around 0 to 1%. Less concerned about the details of this question because you're not going to see something exactly like this on your exam. Did I lose you?
Yes,
There's a piece of information missing from 41, and that's
34 games.
So 4 out of 34. This is the actual proportion.
Okay.
This is what we predicted using the z-score. Our prediction was really close to our actual, so the difference between what we predicted and what we observed was about 1%. Did y'all put something in the queue and I didn't get to it, or did we get to all your questions?
Yeah.
We good? All right, cool. Thanks. Yeah. So this is what we observe and expect is none. 42, 43, worry not. Box plots, we don't talk about in here. Saj, you gonna see tomorrow?
I will see tomorrow.
I mean, or not. I don't know if you got something going on.
No, I'll see you.
All right, cool.
I think it's just a question about Z-scores. Like, I was looking for areas to find the Z-score. There's a lot of 0.499. Like, how do you know which ones to choose?
Gotcha. So let's plant the flag, declare victory, and move on from this one. All right. The next question is, we've got all these 0.4999999 and then a 0.5 here. What's the scoop? We start, when we get z-scores in a normal distribution, When we get z-scores above like 2.9, we start getting in that 3 range. A z-score which is greater than 3 indicates what? It's probably an outlier. So when we start trying to come up with what the appropriate area is here, I mean, you don't choose one at this point. At this point, you're 3.5 standard deviations away from the mean. You may as well call it like half of the distribution. Functionally speaking, that's what we're working with here. Because the normal distribution this line is an asymptote, which means it never touches the horizontal axis, but gets really, 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 really close. And in fact, goes on infinitely in both directions. So I could have a z-score of 100, and the area would still be slightly less than 0.5. But on the order of like a nonsensically small amount, an amount so small you wouldn't be able to make sense of it, hence nonsensically. But as far as we're concerned, effectively, once you get right here, it's like half the distribution.
But just for calculating purposes, like I had to find like a x value, so I had to find the c.
So you had to start with some area, right?
Yeah, which is 0.49 in that. I didn't know which z-score I should use to calculate x from there. Doesn't matter.
Doesn't matter. A z of 3.62 or 3.63, you're already dramatically far away. Like you really are. So much so that I might think that some part of the rest of the process was done wrong. Maybe that like a reasonable thing would be like 49%. 49% is reasonable to start with an area like that for the 99th percentile. But something down here, 49.99, seems a bit unreasonable. Got it.
Just a quick question. Do you have to know like the questions that say like what probably is yes and no percent studying classical empirical subjective?
We did not do vocabulary on classical, subjective, and empirical probability. I will not hold you responsible for that. Ryan O'Keefe. 2015? All right. You've got questions on 2016, spring 2016 that I want to answer? I don't mind taking a quick diversion there. True, false helps me catch my breath. Said 2015, yeah? All right, so cool, 2 seconds. Spring 2016, number 40. Who called dibs on that? Spring 2016, number 40. I wrote it down because somebody wanted it. All right, yours. When we return from the quick aside, you'll drive. We said again, fall 2015? Spring 2015? Spring 2015. Number what? Oh no, false. Change normal to binomial, and it becomes true.
For the same test number 8, if it says the standard normal distribution has a mean of 0 and a dispersion of 1, would it be true, or is the dispersion part that's not?
It's the dispersion part.
Okay. What is
Dispersion is a class of metrics which includes the standard deviation and variance
yes,
and the range.
not dispersion.
Yeah,
So
it's
this is like kind of like that central tendency describes mean.
Yep. Central tendency describes mean, median, mode. Dispersion describes standard deviation, variance, and range. By the way, while we're on this, what is the range of the standard normal distribution?
You say -2 and 2?
Nope. Much bigger than that. We just got done talking about asymptotes. Alex?
It would be negative infinity to positive infinity.
Yeah. It could go on forever. It gets infinitely close. The range, in fact, can go infinitely in both directions.
So, sorry. If this was the same question and it said like, and a variance of 1 or and a,
It could be standard deviation, could be variance, either one is fine.
if it said a mu 0 and a mu 0, that's
Yep.
the standard normal.
Yep. Standard normal distribution has a mean of 0, median of 0, mode of 0. You could probably even, I wouldn't say has a central tendency of 0, because there are probably other obscure metrics of central tendency besides mean, median, and mode, which are different from, but mean of 0, median of 0, mode of 0, standard deviation 1, variance of 1, sort of infinite range. Yeah,
Oh, can I ask one?
you can ask whatever you want.
I'm sorry. The true false, this is general, it's not. That's enough.
All right, I'm going to Dan and then Alyssa.
Could you look at fall 2015 number 7?
Fall 2015, number 7. So we're still running some true false right now, yeah? Another line of these. This is what I know the Cox LAS hate so much. Because they're hard. You cannot calculate the mean of a probability distribution without n and pi. Dan, what's your instinct say?
Is it false because it's not binomial? Or is it just?
That's a good justification. So in a binomial probability distribution, you can calculate the mean by n times pi. That's true. But that's not the proof. No, 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 no. Ah. So this is a probability distribution. And I could calculate the expected value for both payout or net gain because I have a series of outcomes and their associated probabilities. The outcomes are quantitative. To calculate the mean of any probability distribution, you take x times p of x plus x times p of x for all x. I just calculated the mean of this probability distribution without knowledge of n or pi. I mean, certainly I had individual probabilities for the individual outcomes, but things like 20, 15, no, different one. Yeah. That probability distribution we were just looking at, I don't have n and pi. So that's false. What's that?
I get to know the discrete probability distribution of spring 2015
Spring 2015. Which number?
It's like 44.
Well, you'll certainly be asked to read a histogram. You can expect that. Again, this is one where students felt as though I hadn't seen this before, math is hard, I give up. But you've totally seen this before. This is just a histogram. It's just a probability distribution. Thanks, gentlemen. You ready for tomorrow?
I think so.
All right. Well, if you're not, get ready. Thanks for coming by. See you. So we've basically just got two things superimposed. One is if we guess, this is what we expect. Guessing is a binomial probability experiment. On the other hand, this is empirical. This is based on what I saw, knowing that people study. You can still generate probabilities from here, and we spent plenty of time in class looking at distributions. Which of those two distributions, the solid or the stripy one, appears to have higher measures of central tendency? The solid or the stripy? Yeah, the stripes have higher measures of central tendency. It's got a higher mean, it's got a higher median, it's got a higher mode. The mode is 17. 25% of students got 17 questions right. It's just being able to read a histogram, or two histograms in this case, which represent different populations. Some people who would guess, some people who studied. Will you see exactly this? Man, I want to do this one again. I thought this was good. But the pitchforks were sharp and the torches were hot. So I won't be returning to this anytime soon. We're up. Spring 2016, right?
But wait, so this is like, problems like this are not common?
You'll still be asked to read a histogram.
Or not? Awesome.
I mean, that's a histogram. You're responsible for reading a histogram. 2016. You said 40? I think number 10 was on the queue too, so why not? Oh, we already answered that variance question a few times. 40-40. All right. If you've asked me about question 40, please raise your hand. I feel like it's more than just Mitch and Yanni. Okay, good. It's a couple people too. Normally, questions about question 40, say normally because they occur frequently, are which side of the distribution do we mean when we're talking about the top 85% of people? For example, it looks like this. You good, gentlemen? All right, good luck, boys. A couple pieces of information real quick here are the three basic bits. The mean is 100,000, the standard deviation is 10,000, and it's normally distributed. Let's get that onto a piece of paper so we can write. Mu is 100,000, sigma is 10,000. It's normally distributed, and the question says something like, how many hairs cuts off the top 85% of people? So are we talking about a situation like, is the top 85% this, such that 85% is over there, and this is the 85th percentile, or is the top 85% the top 85%, and I'm talking about the 15th percentile. A number of people have asked me about this question, and my answer is as follows. I don't want to ask complicated questions where I'm not able to give you a definitive answer. I think that question is nebulous. I have said from time to time that when students say to me, I don't understand the question, it's the wording, it's confusing. Sometimes that's attributed to the quality of the question, like this. Sometimes it's attributed to the quality of the preparation. If you don't understand the words, the question is going to look like gibberish, so you can blame the question. Here, the question accepts blame because it's ambiguous as to whether I'm talking about the 15th percentile or the 85th percentile. So let me just say, I don't ask them like that anymore. I'm more likely to say, how many hairs indicates the 85th percentile? Or if someone is at the 85th percentile, how many hairs are on their head? Now, the 85th percentile should be an easy position to identify because the 85th percentile is above what percent of other observations? 85. The 85th percentile is above 85% of stuff. The 95th percentile is above 95% of stuff. So if I frame this question as mu is 100, sigma is 10, and I'm normally distributed, what number of hairs, and here I go again, how about how many hairs as opposed to what number? How many hairs is the 85th percentile? Now, if you've done a lot of practice, this probably may not be the hardest thing in the world. If we have, it may still be, who knows? It's getting late. I'm going to draw a normal distribution. Why? Because it says it's normal. And it's not a very good normal distribution because this should run asymptotic to the axis, infinitely. The 85th percentile is over here. And I'm going to have to start with a raw score or a proportion, probability, or percent. And in this case, I'm given the 85th percentile. If I can fill in this value, I will have answered this bueno. If it's the 85th percentile, means 85% below that mark, my table can only accommodate things that look like that. So my next step is to take that 85th percentile and convert it to an area in here. Can you walk me through that?
Yeah, so you know that like from the mean and to the right of it is all 50%.
You want me to go to the right?
Yeah, so like that's 50%. So like at the 85th percentile, that area in that green part is 35%. So it's 0.3500.
Mm-hmm. That's what I get for using a pen. So 0.3500 is the area I'm going to look up in my table. 0.35 gets me 0.1368. No, not that way. Area's on the inside, z-score's on the outside. The area is 0.3500, so I'm going to use the z-score of 1.04. That got me to an area using my picture of 0.3500. I'm no quitter, so I use something close to find a z-score of 1.04 on my table. Z equals X minus mu over sigma. Z is 1.04. Solving for X, mu is 100. Sigma is 10. 10 times 1.04 is 10.4 equals X minus 100. Add 100 to both sides. I get 110.4 equals X. Algebra. And I don't know if the arithmetic is correct, but I know the algebra is pretty solid. I actually set up Hey Siri so that I could start asking her to do my calculations for me, but she only works when she's plugged in. You can't Hey Siri if you're not plugged in. And I don't have her power cord around. Ryan O'Keefe, yes, sir.
I got a question.
I hope I have an answer. Please ask.
US spring 2015 number 10.
I can. Another true false?
Yeah.
Sean, Katie, we good?
Good, thank you.
Yeah, of course. Spring 2015, number 10. Can do. That's the end of this this problem here before we move on. We good? So your comfort level in going from quote unquote right to left on these types of problems should be getting comfortable with language such as the 10th percentile, the 25th percentile, the 60th percentile, and knowing that in a normal distribution, if it's greater than 50, it's on the right. If it's less than 50, it's on the left. Spring 2015. Spring 2015, why were you here then?
Number 10.
Were you here then? What? No, spring, that's a time of year, not a time of day. That was the semester where we had all those snowstorms. You weren't here? So I'm old, I don't have a sense of time. I just know that it was the basement of Harkins, missing lots of snowy Mondays, and a Monday to Thursday class, and just 5 Mondays, which is effectively a third of the course. And it was probably the hardest exam that I offered, so this is the perfect storm. I like this exam though. I think it's better than the others. 10. Well, we already answered this one, right? Female players on the Patriots, it is and the woman. Two parts. The empirical rule applies, ignore this. What's the empirical rule apply to? And only in normal distribution. So this part better be a normal distribution. But this says any distribution that can be converted to standard score. You can convert any distribution to standard score.
Can you go over fall 2015 number 9?
Fall 2015, number 9. Fantastic, number 9. 9 is 10 here? That is around so good. Yeah, good. Awesome. So, gentlemen, we good? Thank you. Cool. Toodles. They're both false. Both of these are false. 9 is false. Knowing that a probability distribution has mutually exclusive elements helps us inform if it's collectively exhaustive. Collective exhaustion and mutual exclusivity are separate concepts. One, mutually exclusive, means that all of the possible outcomes or at least if we're talking about two things being mutually exclusive, that's to say these two things cannot happen at the same time. And that's fine. It's fine for me to know that I cannot land on a head and a tail at the same time. I've said head and tail, and your implication is it must be a coin because that's the language we use. But maybe it's some weird sort of bird die that has multiple sides. And I can tell you that you cannot land on a head and a tail at the same time, or a wing, or a drumstick, or a thigh. Like, you can't land on all these different parts. You only land on one at a time. But until you know that every possible part of this chicken die is included, collectively exhaustive, you don't know whether you can use the complement rule. Sorry, I went complement rule. It's about this. But regardless, those things are still separate. The collective exhaustion says, have I talked about everything that can possibly happen here? Does every outcome that I have listed detail every possible outcome that can happen? But knowing that two outcomes or that all these outcomes don't overlap does not inform me that it's all possible outcomes. So collectively exhaustive, do we have all possible outcomes? And mutual exclusivity, these outcomes don't overlap, are separate. Knowing about one doesn't tell us anything about the other. 10. Primary condition for the application of the empirical rule is what? You can use the empirical rule when what? That's what you should be looking for. What do you find? That the distribution is the standard normal distribution. The standard normal distribution is one of many normal distributions. Sure, you can apply the empirical rule to the standard normal distribution. Why? Because the standard normal is normal. But you can also apply the empirical rule to Providence College basketball, to 96 geo prisms, to... I'm out of examples.
So that should say just normal without the standard.
Yep. Yep. All right. So we are winding down. I know you guys just rolled in, but the update is 4:30 to 6:30 for me, 7:30 to 8:30 upstairs with the rest of the crew. But I can wind down with some short stuff because you emailed these confirmations. Yes, of course. We got the location right, but now we're here. But I can't do this whole thing. Watch that. I'm not here to lay down. You guys stick around. It's 6:27. Do you have specific questions ready for me?
I have one.
All right, let's talk about it. Listen, I don't want you to quit. I don't ever want you to quit. I want you to walk in and think people are walking out so you can't stick around. I told you I want to leave. You want me to stay, you make me stay. I'm still going to leave, but...
Sorry about this. It seems kind of stressful. Sorry.
No. Do you?
Can we just look at 2032 on the training terms?
From spring last semester?
Yeah.
Yeah. I have a feeling that's what Drew and Aiden are going to go over upstairs at 7:30. Well, last semester's midterm. That's what I suggested would be good. So a couple comments on that too is that if 80% of people showed up for this, they're probably not going to show up at 7:30. If you guys show up at 1:05 at 7:30, yeah, it's your own personal powwow. And Drew's quick, and Aiden's used to getting roughed up. So, yeah, you'll have plenty of that time. But we can absolutely answer these questions here. Ryan, what's your question?
Just like for this one, is this false because it says relative frequency, not just regular frequency?
Correct.
Okay, cool.
I was just wondering about the quarters and everything.
We don't talk about quartiles. We did in Q1 in class. We're not going to do it on the exam.
Thank you.
Cool. You ready, Ryan?
Yeah, I think so.
I think so too.
Quería saludar, que eso tiene que ver.
Thank you.
Ahora, a todo el mundo.
Good luck, boys.
Thank you.
Yes.
Cool. All right. 49 is binomial probability experiment. In a binomial probability experiment, there's 3 pieces of information which are essential to figuring it out. N, pi, and x. You happy with that one?
Yep.
All right. In this case, we got this binomial probability table. Depending on the number of trials, how many people am I talking to?
10.
So 10 trials means n is 10. This is the only table I'm concerned about. Now,
Okay, I'll come back. Okay, just keep rolling.
yeah, 20% chance of success means that I'm going to be concerning myself with the 20% success column, that column right there. Easy. They make me pay for what you break. So I break you. You guys ready?
Yeah.
All right. Well, keep studying if you're not.
Thank you.
Good luck. Thanks, Jeff. Of course. See you, John. Here. So in the case of that problem, we said that I'm going to talk to 10 people. There's a 20% chance that they want my card, and then we have a series of questions, right? 29 says how many do I expect to hang out? 30 is everyone, 31 is exactly 1, and 32 is more than 1. Okay? So the questions are 29, how many do I expect to hand out? 30.
So pretty much plugging in this X value into a specific formula, right?
No formulas, tables.
Okay. So
So this is not how we've seen or talked about it before. I absolutely shortcut this from the problem that you see in the thing.
Mhm.
Because the hard part for me, at least what I think, is simply identifying the appropriate X value. Because if I tell you X is 0, so I tell you X is 10. See what I have written for 30?
Yeah.
If X is 10, all you got to do is go N10, pi.2, X10, there's your answer.
so just a little bit slower.
Yep. N is 10,
Yes.
pi is 0.2,
Mhm.
X is 10, there's my answer.
Yeah. Okay.
So it's about figuring out why does X equal 10 in this one. Or in the next one, 31, what does the question ask?
Only one person. Well, exactly one person.
Exactly one person. So X equals 1. It's 10, pi is 0.2, X equals 1.
Okay. All right. So what do we do if it's more than one person?
Is 0 more than 1?
No.
Don't include it. Is 1 more than 1?
Yes.
I'm sorry.
No. One is not more than one.
When it's not more than 1.
So
Is 2 more than 1?
yes.
Which one's 2 in that one?
So do I give the range?
No, you add them together.
Okay. Oh, okay.
But I can do this with this.
Yeah.
And we're gonna have conquer this.
Yeah.
Oh.
Yeah, right?
Okay, I wasn't sure if you were doing that.
So here's another way to look at this, Connor, is that this is a circle. It's a pie chart. It's everything that can possibly happen, right?
Mhm.
It's possible. Let's see. It's possible that no one asks for my card.
You said for card, no, that's for your.
In this problem, it's about handing out my business cards.
Okay.
So it's possible that no one asks for my business card.
Mhm.
And that probability is if n is 10 and pi is 0.2, no one asks for my business card, about 10% or 11%.
Okay.
So it's about 11%. Probability that one person asks for my card is about 27%. Probability that two people ask for my card is 30%.
So it's most likely that two people are going to ask for your card out of any other value, according to the table.
Most likely, according to the table, it's the mode, and yeah. But we could actually calculate this value, and we just calculate it as n times pi, where n is the number of trials. I'm going to talk to 10 people. There's a 20% chance that someone wants my card. So I expect that 20% of those 10 people, which is 2 people, want my card. And as it turns out, this 30% or 0.302 is the mode, is the most frequently occurring of these, because these numbers down here, like 20% probability isn't very high to begin with. And now I'm like, that's the probability that 5 out of 10 or half of the people want my card.
Well, so the one thing that I got a little bit of a problem with, not probability, I know it's very slim, but the table just doesn't list it.
0.
I mean, it's possible, right? That 10 people.
Possible, but not probable. So we're going to still put the number as 0. 0 is what this rounds to.
Yeah,
just round it
so
to
I'm
that
saying
value.
It cuts off. I get that, but
1% is wrong.
it is, it's still a percent. If it's still a chance, it's still a percent.
I don't know why you're arguing with me on this. The answer is 0. Well, it's smaller than 1%. So small that to say 1% is more incorrect. So think of it like this. If I said 19.1%.
Yeah, no.
It's closer to 19, so you call it 19. 0.0000001 is closer to 0 than 1, so we call it 0.
Yeah, okay, I understand.
You can't call it 1.
All right, well, I think that gives me a solid base, so I appreciate that. Thank you.
If you have the opportunity,
we thought it was until 7:30.
yeah, it was till 7:30 earlier, and then.
But you have a life too.
Well, there was just some miscommunication and coverage, but for what it's worth, I'm still here. So I want to point out one thing though, is that I got this. So there's video which is available. It's probably a good idea to revisit if you can sort of jump through till you get to the point where we start talking about hockey and Tuukka Rask, and Victoria and I were chatting about this a little bit too. Like, Connor, you play some sport?
I'm a washed-up high school athlete.
Okay, so
I did.
Give me sport. Did you put the ball in the hole? Did you put the ball in the square?
I played football.
Wonderful. So, like the defense has a responsibility, the offense has a responsibility. So if you're a goalkeeper, your responsibility is keep the puck out. If you're a defense, your responsibility is keep the ball out. And we can think about success and failure, because pi is success probability. We may be in a situation where we think about, and this is the Tuukka Rask problem.
Was this on the YouTube link?
Yeah, you'll be able to find this discussion previously, but I want to give you the short version of it right now. To recognize that if Tuukka faces 10 shots and his save percentage is 90%, you expect him to stop 9 out of 10 shots, right?
Mm-hmm.
But that also means that he could potentially allow 1 goal in 10.
Okay.
So if there's a question where we know this is his save percentage, and I say, what's the probability that he makes 10 saves? N is 10, pi is 0.9. X is 10 because I want to know that he makes 10 saves. I could also ask, what's the probability that he allows 10 goals? N is 10. Pi is 0.1 because that's the probability that he allows a goal. Low proportion of time he allows a goal. 10% chance that he allows a goal. But
Wouldn't that be the same answer?
those are the same answer.
Okay.
These do provide exactly the same numbers. We can look at the table in a second, but this
Okay,
is
all right, yeah, I know what you're saying.
10 stops, probability of stopping, or no goals, probability of a goal.
So it's the same question too, pretty
No,
much.
no, it's not.
Well,
It's
Sort of.
no, it's a
You just-
different question, but the probability is the same thing.
yeah, these values, 0.349, which is pi is 0.1, x is 0, is the same thing as pi is 0.9, x is 10.
How did you know to link up 0.10 with 0 and not the other way around, and not 0.9 with, you know what I'm saying?
Because that's the values you gave us.
So there's a verbal linkage here because I know this is save percent and I want to know he makes 10 saves.
Oh, okay, I got you.
This is goals allowed percent
Okay.
and this is 0 goals.
I got you.
And it's whether we call it, and I think sports is great here because it's a goal or it's not. It's one or the other. It's success or failure. You love it but if there's a 10% or a 90% chance that you love something, maybe there's a 10% chance that you hate it or something like that.
Gotcha. Is that, we phrase that or ask in different ways? Like, is there more questions that go along with that? You know what I mean? Is it just gonna be what's the chances he saves it or he lets it go, or is there more you can ask?
That's kind of what it's like on a practice exam, so I'm gonna assume that what he's preparing us for, I don't think he would
I don't know.
necessarily think
I was just
it's
asking.
jerky.
Yeah, no, I'm not trying to jerk you around on this. But like this is the relationship between those things and it's the same number. And you might encounter something in the realm of binomial probability where they're complementary as in 1 minus. Your save percentage is 1 minus your goals allowed percentage.
Yeah.
Or we talk about, pitchers in baseball may have ERAs, but there's a batting average that a batter has or his failure rate, which is the complement of his batting average. It's weird. Baseball's a game of failure.
It's a game of stats.
Oh, it's so long. There's so many observations.
Are you a big fan of Moneyball?
It took me a long time to ever just encounter it. People were like, you should watch that. I was like, okay. But I don't know why I didn't because I love all the actors in that movie and it's sports and it's stats and it's retro.
It's drama.
It is great.
It's an awesome
It's
movie.
a great movie. I love those sport highlight movies that gives you chills and you're like, I know it's going to happen, but I hope the A's win the pennant. You should turn around and go to that game.
All right.
I think it's good. I think that movie's good because it also gives you a window into the administration of baseball, and other sports, which they don't normally do. Which I think is a good thing.
Yeah. Well, if you guys
Appreciate
want
that.
to stick around, I still got to wrap some stuff up, and I can talk to you casually as I do so. But for now.